Okay, so we are going to get started with an example. I know I have here for you all to try it first, but we'll run through this. We'll run through this example, and I'll give you a question to try on your own. Okay. So we have here a cylindrical glass rod in air has refractive index of 1.52. One end is ground to a hemispherical surface with radius r equal 2.00 cm as shown in the figure below. Given that the refractive index of air is 1.00, determine the position of the image for a small object on the axis of the rod 8 cm to the left of the vertex x as shown in the figure above and the linear magnification. So in this case, they're asking for the image of the object to the left of the vertex. So we are just considering one refraction alone. So we use the equation n over s plus n prime over s prime is equals to n prime minus n over r. From here we have n is equal to the refractive index of air, which is 1.00, n prime, which is the refractive index of the glass rod, and that is 1.52. We want to determine the position of the image, so we want to determine what s prime is. This is our unknown. We are given s. S is equals to 8 centimeters. Now, your object is to the left of the vertex, right? So it means that s is equal to a positive 8.00 centimeters. Our radius of curvature, this is a convex surface. If we are looking at light from the object is going to be moving from left to right. So this surface bulges out, so this is a convex surface. Right, so I'm just going to put a note here, convex surface. So my r is going to be positive because the center of curvature is to the right. So this might be my center of curvature to the right. So my r is going to be equal to positive 2.00 cm. Now for all of your optics questions, you want to sketch the diagram, you want to put in your object distance, your refractive indices, and your radii of curvature before you start with the problem itself. Now we could make our substitutions. So n is 1, so we have 1 over s. S is going to be plus 8, so we put 1 over 8. We are working with centimeters throughout, so I can temporarily drop the units. So I have 1 over 8 plus n prime, which is 1.52 over s prime. S prime we don't know, that is what we want to find out. And this is equal to n prime, which is your second medium, minus n, which is your refractive index of the first medium. So we have 1.52 minus 1.00 divided by r, and r is plus 2, and we can rearrange this equation and solve for s prime. So we have 1.52 over s prime is equal to, the left hand side here is 1.52 minus 1, which is 0.00, 1.52 divided by 2 minus 1/8, so minus 1/8. And this works out to be 0.135. So S prime is equal to cross multiply 1.52 divided by 0.135, and this is equal to 11.6 centimeters. And don't stop there. Your image distance is 11.26 centimeters, right? So you're going to give a statement. The image forms 11.26 centimeters to the right of the vertex X. We also want to note that the image distance is positive, and therefore the image is a real image. Now we want to determine magnification. So magnification, this is for the second part of the question. Let's just go back here a bit. We want to get the linear magnification. So m is equals to minus, remember it's always going to be image distance divided by object distance. But when you have a refracting surface, you have to accommodate for the refractive indices. And your numerator is going to be your refractive index of your first medium, and then your denominator is going to be the refractive index of your second medium. So m is going to be equal to minus, our n is refractive index of the first medium, which is A, 1.00, multiplied by S prime. S prime here is positive 11.26 centimeters, divided by n prime, which is the refractive index of the second medium, which is 1.52, and S is the object distance, which is plus 8.00 centimeters. When you work that out, you get linear magnification to be minus 0.93. And what does this tell us? This tells us that since m is negative, the image is inverted, and since the magnitude of m is less than 1, the image is diminished. So we can put a statement, since m is less than 0, meaning negative, the image is inverted. And since the magnitude of m is less than 1, image is diminished. And remember, this is in comparison with the object. Right, so the image is inverted in comparison with the object as well. So I don't know if you all have questions on this particular example. upload these slides for you all so that you can review it in conjunction with the recordings underneath your Blackboard Collaborate section. And for the rest of the course, we will be dealing with mainly multiple surfaces, right? So we'll do an example of that in another session. What I would like for you to do for homework is to review example 2 of chapter 2 of the Pedrotti. Now they didn't really form it as a question, so I have put it in the format of a question. Right, so in this case you have a thick convex lens. So you have a real object, it's positioned in air 30 centimeters from a 10 cm thick convex lens, whose surfaces have a radius of curvature of 5 centimeters. To the right of the interface, the refractive index is that of water. Determine the nature of the image. Okay, I think I didn't complete this question, right? Let me just complete the question here for you. I'm just going to go back to the Pedrotti and check. Now, in this case, all you're doing is applying what you did for one surface to multiple surfaces, right? So I'm just rechecking this particular question because they really didn't form it as a full question, right? Okay, so okay, so this lens here is really a lens of water. So what you're going to consider, you have air on one side, you're going to have water here inside this convex lens, and then you're going to have air on the next side. And you're looking at how this thickness here is going to be 10 centimeters. The object is going to be at 30 centimeters from the first surface. So for this particular question, you have to consider where the image forms due to refraction for the first surface. So we call this S1 prime, might form somewhere here in the water. And because you know the thickness of the lens here, this image acts as an object for the second surface. Right, so you have S1 here, which is 30 here. You'll have to find S1 prime, which is the image distance. This acts as an object for the second surface. So you'll have a S2, and then you have the final image forming outside, possibly outside or inside the water itself. So I'd like for you all to review this from the Pedrotti. So that's one question. And then a rather more interesting part, well, at least for me, is to show that if you have a thin lens of refractive index N2, and this thin lens has a radii of curvature R1 and R2 suspended in a medium of refractive index N1, we want to show that the thin lens equation is given by 1 over S plus 1 over S prime is equal to N2 minus N1 divided by N1 into 1 over R1 minus 1 over R2. In fact, this entire right-hand side here is equal to 1 over F. Oh, okay. And then you also have to derive an equation for magnification and for the focal length of a thin lens. Right? So this, you have to show how 1 over F is equal to this part of the equation. And when you write it like this, you get back 1 over U plus 1 over V is equal to 1 over F, which is what you learned in CSEC. So essentially here you are showing that 1 over the focal length can be expressed in terms of the refractive indices of the medium or the different media, and as well as the radii of curvature of the two different surfaces. I don't know if you all have any questions. If you all have questions, please do share. If you have any comments, also please do share. And then we will break for the day. Okay, if we need to upload our solutions, no, you don't have to upload your solutions. What I will do is that I would like for you all to try it first before I upload a solution. Right, and the reason why I would like for you all to try these things first is because it's a process and it's a logical process with particular steps that you have to follow. Right, so the chapters for suggested reading is chapter 2, Geometrical Optics, for by the in Pedrati. This is the I think this is the third edition. I think I had provided some links for that, right? So for your homework, what you're doing essentially is taking what we derive for refraction at a spherical surface, and now you're going to put together two the thin lens equation. But before you actually do the thin lens equation, you'll need to try the first question. Right? It's there in the Pedrati. The solution is there in the Pedrati, right? So I want you all to try this particular question first before you do the proof for the thin lens equation. And while I will be putting up solutions for you to review, you do need to practice the method for approaching these questions, right? So what we did as an example was for one surface, and you're going to try the question for two surfaces and do the derivation again for two surfaces. This practice is important for the next part, which is on using the matrix methods to do the same analysis. And you'll see that the matrix methods is a little bit easier than using this particular method. Right, so essentially we're going to be building on every consecutive lesson. Any other questions? And before I forget, do review the solutions for the last set of questions on worksheet 2. Okay, so that's it for today, and I will see you on Friday. Okay, bye. Thanks, Dana. Yes, I will get better, much better.